Okay, so today we're looking at a problem called populating the next right pointer in each node. Essentially, we're given a perfect binary tree where all the leaves are on the same level and every parent has two children. This is really important because this makes the problem a little easier to do. Take a look at example one here, and actually before we go there, take a look at the node structure. So what we're trying to do is we have this next pointer that's unpopulated at the moment, and we need to populate it for each node. So now let's look at example one. As you can see, we're given something like the following tree, and what we need to do is we need to populate their next pointers such that each adjacent node becomes their next node. So visually, it's pretty easy to understand what they want us to do, and there's really only two approaches I can think of how to go about solving this. These are really the two that should come to your mind as well. The first approach is a breadth first search. This is where we'll go layer by layer. So layer by layer seems like it'll be pretty easy. And the other approach is depth first search. In this one, we'll go vertically all the way down and then work our way up and then all the way down, work our way up. So it's a little bit trickier, but we're definitely going to see both approaches and see the trade-offs as well. So let's start off with the breadth first search solution. I feel like this one's a little easier to understand and will make it easier for us to understand the depth first search. The main differentiator between BFS and DFS is really the data structure we're working with. With BFS, we have a queue where the properties of a queue is it's first in, first out, so it comes in and it goes out first. Whereas when you're working with a stack, it has the following properties of last in, first out. So as the stack builds up, 2 and the 3 comes in, it's the first one to come out. Whereas over here, if the 2 came in and then the 3 came in, and now we pop, the 2 is the first one to come out. Now for our problem, we're actually going to be using one more variable, and that is the prev variable. The prev variable is just going to hold the node so that we can actually build this next pointer. With all of that said, let's work through example one. So the queue starts with the one already pre-populated because that is the root node. What we're going to do is we're going to pop the current node from the queue, and then we're going to populate its next pointer. Prev is initially set to none because that's where we're initiating it at. So one's next pointer will now equal null in this case, or none. And then we're going to update prev to the current pointer. Upon doing this, now we need to add its children. Now, one question you really need to ask yourself is, do we first add the left child into the queue first or the right child? And I think in this example, it makes sense why we would do the right child first. What we really need to be careful of is if you take a look at the second layer here, prev is currently going to be equal to none. So when we take the right pointer, we can easily set its next pointer equal to prev, which is null, and then update prev to this current pointer. That way, when we go back to the 2, prev is now equal to the pointer before it, which was 3, and we can easily build this relationship. Had we not done this, what would happen is if we had added the left child before the right child, prev is equal to none, so we would set 2 equal to none first, update the prev pointer to the current pointer, which is 2, and now when we go to the next pointer, which is the right child of 1, 3, we'd end up setting it equal to 2, which builds the opposite relationship that we were trying to achieve. Okay, hopefully that tangent made a little bit sense. So right now, so far we populated the next pointer for the root, and we've added their children such that it's 3 and 2, the right child before the left child. None is always going to start off with an initiation of none, and we're going to work through the second layer. We pop from the queue, the 3 comes off. Upon popping the 3, we're going to have to set its next pointer, which is equal to prev. So 3 now points to none. Now we need to update prev to the current pointer, which is 3, and we move on to the next node inside the queue. With the next pointer now populated, we need to do the same thing again. We need to add the right pointer before the left pointer. And so the queue is going to grow. So the queue now looks something like this. Finally, with the 3 off the queue, we're going to move on to the next node, which is the 2. We're going to do the exact same thing. We're going to populate its next pointer to equal the prev variable, which is 3. So 2 now points to 3, and we're going to update prev to equal the current node, which is 2. And again, we're going to add the right node before the left node. So 5 and 4. With the 2 off the queue is now empty. We're going to start our next loop. At the start of the loop, set prev equal to none, and let's pop the first element, 7. It's going to be the same thing again. We're going to set its next pointer equal to prev, which is none, so it points to none. Because it doesn't have any right or left child, we don't need to add anything more to the queue. We just simply move on to the next node, and also make sure you update prev so that's the current node. Pop the 6 from the queue. We set its next pointer equal to 7. We update the prev equal to the current node. No children, so we don't add it. Do the same thing, 5 and 4. Pop 5 thing. Set its next pointer equal to prev, which is 6. As you can see, that's how we built that one relationship. Set prev equal to the current node. And finally, the same thing with 4. Pop it from the queue. The queue will now finally be empty. We're going to set its next pointer equal to 5 and set prev equal to the current node. With the queue finally being empty, we can finally exit from the loop and return our root node. To evaluate the time complexity for the solution, it's actually not that difficult. Because we go through the entire tree and we touch every node once, it's O of n for the time complexity. However, for the space complexity, you may be tempted to say it's O of n as well. However, because this queue is always getting longer and shrinking, at most, the total size of this queue will be O of w, where w is the widest region of the tree. So like this very bottom part of the tree. Let's now work through it on LeetCode. So following our example, pretty simple. We're gonna first create our queue. Just gonna name it queue, and we're gonna initialize it with the root. Actually, this needs to be in brackets. Now, while the queue is not empty, we're going to first do two things. We're going to initialize our prev variable, which is equal to none, and we're actually going to just grab the size of the current queue. And this will make more sense in a bit. So remember that we pop the elements out of the queue and we set their next pointers. But as we're doing that, the length or the size of the queue also grows. We want to make sure we go layer by layer, so that's why we're grabbing the size of the queue. Okay, so now let's loop over the elements inside the queue. So for I in range, length of queue size, we're going to grab the first element in the queue, pop left. Remember, this is a queue and not a stack. Let's populate its next pointer equal to prev, and then update prev to the current node. After doing that, we're just going to go ahead and add the children. So first we're going to add the right child like we did in our example. Okay, and now we're going to add the left child. Here I'm just checking that the right node does exist. That way, if we get to a leaf node, we don't end up adding none to the queue. And finally, we can return the root. Now, one check you also have to do here is the root that's passed in can also be empty. So in case that's the deal, we need to make sure we check that and return none. And you can do that easily in Python like so. So this is our final solution. The time complexity is pretty simple. We use a breadth first search approach where we touch every node once, and the size of the is at most the total width, the maximum width of the tree. Okay, now let's work through the depth first search solution. This one's just a little bit trickier than the breadth first search, but I don't think it's that hard either. If anything, I think this one might be more intuitive. There's actually two things we need to ask ourselves before we do this. The first question we need to ask ourselves is, these links, should we be creating these as we go down the tree recursively? Or should we create these links um, bottom up? Essentially, first we go all the way down to the tree, and then we build these links as we backtrack our way back up. The second question we need to ask ourselves is, should we start by recursing on the right side of the tree, like we did in the breadth first search solution, or can we start on the left side this time? Or does it even matter? So let's answer that first question, whether or not we should create those links as we come down or come to the leaves first and then build those links back up. So, I mean, what you need to ask yourself is, imagine you're on this layer right here and you're on this 5 node. How can I possibly build this link between the 5 and the 6? How can I get the reference to this node right here? To me, the only way that seems possible is if we already had a link up here where our root node has the following link to the next node, 3. That way I can grab this 6 node by referencing my root node, going over to the 3, and then grabbing the 6. So maybe that means we should probably build these links as we come down the tree. Now regarding the second question, does it really matter if we come down the left or the right hand side of the tree? I think over here, it doesn't really matter which approach we take, but it might actually be more beneficial to go down this route if this tree was not perfectly balanced. Because you can imagine where this 6 node does not exist. So actually, I drew out this tree to better explain the idea. So you can imagine if I was on this layer right here, and I was at this node, and I wanted to connect it to the node at the very end here. How could we possibly do that if we went down the left tree first? It's not possible because this next pointer right here, this one will be populated at this point, but the pointer over here will not have been populated. So the only way we could have grabbed that and grabbed this node and gotten that reference would have been only possible had we gone down this tree on this end to begin with, on the right side first. Now I know the problem isn't that complicated and isn't asking for this, so we can ignore it, but I think it's just helpful to know and recognize this potential lookover. This could easily be a follow-up question and could make this problem significantly harder. Okay, so let's just work through example one and simulate what will happen in code. So we're going to start off with the root node to begin with. So we know that it has both a left and a right child because it is perfectly balanced. So the very first thing we need to do is grab the left child and set its next pointer to the right child. Simple, easy. Now for the right child, we need reference to its root node, which is the 1. And before we set its next pointer equal to something, we need to check if the root actually points to another node. In this case, it'll point to none, which is okay. So we don't really see it come to play right now. Now we recurse down one of the paths. Let's just recurse down the left path. Now we're at the second node with the root node. We're going to grab its left child as well and set its next pointer equal to the right child. Now, to set the right pointer of 5 to 6, we're going to grab our reference to the root, which already has a reference of the next pointer set to the node 3, and we're going to grab its left pointer. That way we can set this relationship that we're trying to achieve here. So I know that's really where the tricky part of this problem comes in, especially when we're working with DFS. It gets a little bit confusing, but hopefully that made sense. And then, I mean, the right-hand tree is just as simple. We're gonna, so let me remove all this. Now when we're on the right-hand side of the tree, we're gonna grab its left pointer, set its next pointer equal to the right child, And because its next pointer equals none, there's nothing we need to do for the right hand. Finally, let's evaluate the time complexity for this solution. Now, again, like the BFS, we touch every single node inside the tree, so that is an O of n time complexity. But once again, the space complexity is a little bit more tricky. Because we're recursing down the tree, at most, the most number of nodes we can expect to be in the stack is the height of the tree. So over here, the expected space complexity should be O of h for the height of the tree. Okay, let's work through it on LeetCode. The way I like to write my depth first search is I like to have the helper function inside of the main function, so we can use it directly. Okay, so with the DFS function created, it's going to take the current node as a parameter. Our base case that should end the recursive calls is when the node is equal to none. So we've reached the end of a leaf. So if not node, simply end the recursive calls here. Now, just so it's easier, let's grab the left and right nodes of the current root. Now let's go ahead and set the left node's next pointer equal to the right child. And for the right, before we set its next pointer equal to the right to the next pointer, we need to check that our current node, so our root, has a next pointer. We could be at the end of a node like in the 3 over here, in which case the next pointer is just null, so it doesn't really have any children. And then we can set the right pointer's next pointer equal to our current root's next pointer's left child. Finally, we're going to do our recursive calls. So do that on both of the children. Does not matter if we do the left first or the right. However, I would say doing the right is a little bit better. Then we can return our current node. We also need to check that the left and right child are not none. This is for when we're at one of the leaves. Okay, and I think the time complexity makes sense. We touch every node once. Space complexity is the total height of the tree. All right, I'm going to leave you guys with a follow-up question like I always do. And I've already given you a hint to this problem, but this time you're not guaranteed that the tree passed to you is a perfect binary tree. It could be a skewed tree, it could be, it's just, but it is a binary tree. It's just not a perfect tree. And you're going to try to achieve the same property we have here where you populate these next pointers, but you're obviously going to have these gaps in between, like I showed you in the example.